All right, so today what we're going to be talking about is a new type of function, okay? And this, again, the reason that we're going to really approach this in different ways, this is very much a different type of function that we've been working with before, okay? So this type of function is what we call an exponential function, okay? Now, the reason that this one's different is the parent equation we've always been doing, or everything that we've done has been like x to the first, or x squared, x cubed, cube root of x, square root of x, so on and so forth. So everything we've been doing has been doing something with x to the some power, essentially, okay? For this family, or for this parent equation, the reason that this one's different is if we're going to have f of x is equal to 2 to the power of x, okay? And again, why this is different is we're now having a base value, right? And then it's 2 to the power of x, but also this base value, this is not like our parent function is not necessarily going to be our parent function. And you'll understand what I mean when we start looking at, like, what about 3 to the x, 4 to the x, 5 to the x, so on and so forth, right? This parent function is essentially going to cover all of those. And you'll see what changing that value, that 2, right, what effect that's really going to have on the graph, okay? So we're just going to start off graphing this like normal, but we're going to use a table of values first, okay? And again, we're going to start off the same place that we started off with every single function. We're going to say, okay, what happens when x is 0, okay, because that's the easiest place to start. Well, if x is 0, that means this is f of x is 2 to the 0. And what's anything to the 0 power? What? It's not 0. It's 1. Anything to the 0 power is always going to be 1. Okay? So my very first point, again, this is why it's different. We've been starting off at the origin almost every single graph that we've looked at. This is the first one that's not actually going to cross at the origin in the parent function. Okay? So again, now we want to look at what happens to the left and to the right. So we'll start with -1. Let's start with the left side first. Okay? So if x is -1, right, that means this is 2 to the -1 power. And what does it mean when we have a negative exponent again? What's that? It's a fraction, so it moves it into the denominator. Okay? So we have 2 to the -1 is the same thing as 1 over 2 to the 1, which is just simply 1/2. Okay? And again, I know this is kind of a small graph, and it's really tough to kind of get that about a half. But it's going to be somewhere around there. Okay? All right. Now let's look at what happens when we go to the right. So let's just say x is 1. Well, this is 2 to the first power, which is just simply 2. So when x is 1, y is 1, 2. So already we can see this is nonlinear, okay? Because if I look at the slope between my when x is 0 and x is 1, right, it's got a slope of 1. I go up 1 over 1. But if I look at when x is -1 and x is 0, our slope is actually 1/2. Okay, so we have different slopes. Obviously, this thing's going to be a little bit more curved. Okay, but we need more information, so let's look to the left a little bit more. Okay, let's choose x is -2. Well, this is 2 to the -2 power. Which, remember, negative exponent means it moves it from the numerator to the denominator. So this is now 1 over 2 squared, which is 1 over 4. Okay, so even smaller, in fact, it's actually exactly half as small as the one before. Okay, so now our slope's gotten even tinier. Well, let's look what happens to the right-hand side. Okay. And so now I have, this is 2 squared, which is 4. So if x is 2, y is now 4. So it's actually getting, so our slope on the left-hand side is getting tinier and tinier, but our slope on the right-hand side is getting much bigger and much bigger, okay? So let's try it one more time with, to the left, let's go -3. Right? Just again, we want to kind of get a little bit better shape of this. And we have now 2 to the -3rd, which is the same thing as 1 over 2 to the 3rd, which is 1 over 8. So we're even closer to that x-axis, okay? And then if we look again to the right, if we look to 2 to the 3rd power, this is 2 to the 3rd is 8. Okay. Oh, yeah, 2 to the 3rd is 8. So now, oh, sorry. Yeah, so I've gone over 3 and up 8. Now, if we look at what happens if we take 2 to the 4th power, that's 16, and we're not even on the graph anymore. Okay. And so you can kind of see what this guy looks like, but I want to kind of ask. So to the right, we know that this thing's gonna keep going up and up and up and up and up. Okay. But what's going to happen at the left? So I want you to think about, okay, where do you think this thing will cross the x-axis? Okay, because it looks like it's getting really close, but it's not actually touching so far. So I want you to think about that. What does it mean when it crosses the x-axis? What value does y have to be in order for my graph to cross the x-axis? 0. It's got to be 0, right? But the problem is 2 to what power will ever give me 0? Nothing, because if you look at 2 to the 0 power, that's 1, so that's not going to give me 0. If I look at negative values, all I'm doing is getting fractions that are just getting smaller and smaller, but when will that fraction ever become 0? It won't. So this thing's going to get really, really close to the x-axis. It's going to get super close, but it's never actually going to cross it. Who remembers what that's called when we have something like that? What? Asymptote, right? It's called an asymptote. So here at the x-axis, since we can never cross it, right, we actually have a horizontal asymptote, okay, at y is equal to 0, okay? So you can kind of tell me what this, so again, for the verbal description of this graph, you can kind of tell me anything that you want to about it. You might say something like this looks like a ramp, or anything that kind of helps you identify what this graph looks like. I may mention the asymptote in here, right? But now let's kind of look at our defining characteristics, okay? What's the domain of this function? Okay. So for what values of x is this thing defined? Negative infinity to positive infinity. It's always defined. Now, I can choose any value of x, and I'm going to get for my input, and I'm going to get something out of this. Okay, so my domain is going to be negative infinity to positive infinity. What about the range, though? The range. Remember, domain is talking about like my x values that I can get. It's the range. The range is talking about my y values that I can get. What's that? 0 to positive infinity. Okay. Now remember, my graph can't ever actually equal 0. So instead of a bracket, I'm going to have a parentheses for 0, and then it's going to keep going up and up and up to positive infinity. Okay. Now this one, my function is it constantly it's increasing, right? If I look at this guy, it's increasing everywhere along the domain. It never looks like my slope is always going up. Okay? So since it's always increasing on the domain. Okay? Now, obviously nothing radicals, like our graph is our function's pretty simple, so our graph isn't going to go up to 2 million and then all of a sudden do some weird erratic thing, right, where it starts decreasing, right? we're just going to always have an increasing function, so this one's never going to be decreasing. Horizontal asymptotes, right? Remember, horizontal, think about horizon, right? It's the ones that kind of tack at y values. We have a horizontal asymptote at y equals 0 in this case. And now for vertical asymptotes, it looks like, right? Again, it looks like we're going to go up and up and up, and it might have a vertical asymptote. But the truth is right, we're going to keep going up, and we can choose any x value. So there's no x value can't equal, right? So this thing's not going to have any vertical asymptotes. Okay. X-intercept. Okay. In this case, right, we have none. But I want you to think about, okay, let's think about if we transform this guy and we just kind of shift it up or shift it down. I want you to think about, like, what happens if it's, like, for our function y is equal to 2 to the x, let's go minus 3. If I had something like that, how could I find the x-intercept? Because, I mean, realistically, what you want to do in order to solve for the x-intercept is this. And, instinct will tell us, okay, well, I move the 3 over, and I get 3 is equal to 2 to the x. But how do I solve for x in this case? I don't want to take the xth root of something, do I? No. So how might we do that? So we're not going to talk about that today. Right, that's definitely going to be something that comes up later. Right? So I want you to understand that we will come back to this. Okay. Now for y-intercepts, right? For y-intercepts, we already know where it's at. Right? That was the very first point we actually plotted. Right? We know our y-intercept is at y is equal to 1. Okay? And again, how we solve that? Y is equal to 2 to the 0, which is equal to 1. Okay? Now, we know this thing doesn't have a max value because it's just going to keep going up and up and up and up and up. But what about a minimum value? Why are you shaking your head, Russell? It doesn't matter how far down how close I get to the x-axis, right? I can still find a value that's going to be smaller and smaller and smaller and smaller and smaller. So even though I have this asymptote, right, that says, hey, we can't ever go below 0, right? I can't ever actually find what value, because remember, when we talk about minimum and maximums, we're saying, hey, this is the point that my graph will never, that is in my graph, and it'll never go below. But since 0 isn't part of my graph, I can still find stuff that's smaller and smaller and smaller, but never actually getting 0. We don't really have a minimum, okay? That 0 is kind of like a false minimum, okay? So we're going to say none, even though I can't, Mr. Kiefer can't write today. Okay. Now, 1-to-1, remember, okay? If I do the vertical line test, right? If I go from left to right and my graph doesn't touch in more than one place, right? This thing's a function. So we know that this is a function. Now, for 1-to-1, right? We have to use the horizontal line test. So, is this thing 1-to-1? What do you guys think? Yeah. All right, pass the horizontal line test, so this thing is 1-to-1. Now, if you remember from last unit, right, this means that, hey, this function's 1-to-1. We actually have an inverse. Okay? Because it's 1-to-1, we know that an inverse is going to exist. What do you think the equation for that is? Because if I think about it, if I have my function here, f of x is equal to 2 to the x, if I wanted to find f inverse of x, right? I'm do my little arrows here. I make this as y is equal to, not 2x, 2 to the x. And then I switch the x and y's, and I get x is equal to 2 to the y. But how do I solve for y in order to find that inverse? Right? Again, questions for later. And we will come back to that. Don't worry. We will definitely come back to that. Okay? For slope, just like normal, it's nonlinear. Vertex, unfortunately, guys, there is no h and k in this one. There's no vertex at all. Nothing in here acts like a vertex. Right, the y-intercept is probably going to be our most intriguing thing, but we'll talk about that later. Axis of symmetry, this thing is clearly non-symmetrical. Okay? And that's kind of the gist of this. Now, as far as transformations, we're not going to explore transformations of this guy as we typically do. Okay? But I'm going to show you a little quick Desmos, and I'm going to introduce the equation, which is definitely going to look a lot different than what you're used to. Right? So for transformations, and I'm just going to make a little note at the bottom here. Right? Our HK and A and stuff are still going to act the same, but for this one, it's going to be A times B, so our different base, to the x minus h all plus k. So this definitely looks so much different than any one that we've ever come across. But tell you what, our h and k and a, they're all going to do the same things again. Nothing's going to change as far as that's concerned. Okay? However, just understanding that things are going to be very different, and that b is going to play a huge role. And again, I just kind of want you to watch right now to see what they actually do. Okay? Oops. Yikes. Okay. So here we have our parent function. Okay? We know we have our horizontal asymptote at y equals 0. In this case, k is 0. Okay? Now watch what happens when I change the base. So b is, I guess, that's the easiest way to think about it. B is base, right? So my base in this case is 2. So this is my parent function. So watch what happens when I change b and make it like 3. Or 4, 5, 6. What's happening to my y-intercept? Nothing. It's staying the exact same. It's still, this point, 0, 1. But my graph is just kind of getting steeper and steeper and a little bit more essentially right-angled, you could think about. Okay? So that's really what's happening with b, is that's all it's really changing. Okay? But what happens if b now becomes, if I go less than 2, right, we still have this, but what happens when I get to, this is why we didn't look at 1. 1 to the x. Because it's always going to be 1. 1 to any power is always 1. Well, same thing with if I go down to 0. It's just 0. Okay? But notice, did you guys see kind of what interesting thing happened when I went between 0 and 1? And then what about negative? Oh. Interesting. If b's negative, nothing happens. Weird, right? Weird. Food for thought for later. Okay? So we're going to stay with 2. But now what happens if I change A? So remember, A is my horizontal stretch, or my vertical stretch compression. But B kind of looked like it did that too. Okay? So as I increase A, but now look what happened to my y-intercept. Where is it? So if A is 4, if this thing will let me, my y-intercept becomes 0, 4. Okay, well, let's look at what happens if I go, less than 1. All right, it's still decreasing, and then I flip it, and now I have, I still have the reflection. So A still acts the same. Just the interesting part about this is where my y-intercept is now. So it's not HK or anything like that. Our new y-intercept becomes whatever A is. Okay? And then H, right, still moves it left or right that many units. You get that? And K does the same thing. But notice where my asymptote is when I move K. My asymptote shifts. Okay? So my asymptote is wherever K is. So when K is 0, it's y equals 0, the x-axis. But if I start moving K around, right, y changes. Or my horizontal asymptote changes. All right, and we'll talk about growth and decay in just a minute. Okay, but you do have this Desmos if you'd like to look at it and kind of play with it around a little bit later. Okay? But again, we're not going to graph these transformations like we normally do. Okay, we're going to look at a little bit more, I guess, simpler, because it's really not simple. It's still complicated. Oh, whoa, whoa, I don't know what I just did there. Ah, no. Stop. What is happening? Yeah, no. Yeah, no. Okay. Here we go. So now I want you to do, nope, that's the wrong one, sorry. Where's the graphing one? Here we go. All right, graphing. So go ahead and get this one out. I'm going to give you guys just a minute, and I'm going to stop the video for just a second. I'm going to break this up and do a couple of videos. So before we move on to this one, I want to give you guys like a minute to try or to get this one out. And please keep watching the next video in order to look at this one.